So good afternoon, everybody, and good daytime, when you're listening to that online or remotely. I won't explain much about the title, but for those who want to follow along, you can find all my talks, or most of my talks, on my GitHub, as well as the slides from this talk. Now, a little bit about me, just to give you, I'm a very privileged person. I had the chance to learn from really very good people, and I had the chance to start C++ even well before the Berlin Wall fell. And talking about Berlin, we're now 10 years in Berlin, and I was speaking at Meeting C++ even before it moved to Berlin. I remember my first C++ conference, it was 1992 in London. It was the European C++ Users Conference, or Users Group Conference, or something like that. I think it migrated to become ACCU, but I'm not quite sure about the history because I lost track a little bit about that. But nevertheless, that was my first attending a conference, and I started speaking at conference for other topics, not C++. Soon after that, I was dragged into WG21 by Alistair Meredith from ACC. At ACCU, he talked to me, well, Peter, you're asking so good questions about C++, why don't you join the committee and ask the questions there? And that happened, and I managed to contribute to all C++ standards, very tiny pieces, since C++ 11. I'm even proud that I contributed to the latest C standard, and it was a very tiny change, substituting a letter with 3 dots. So I'm proud of that. I was privileged during my time to actually learn from a lot of people. I co-authored 2 books on pattern-oriented software architecture, the volume 1, and security patterns, and also provided some input to others. In the recent past, or let's say the past 1.5 or almost 2 decades, I worked with my students and assistants on C++ refactoring, and I'll talk a little bit about that later on. And I also contributed to safety standards for C++, like the recent MISRA C++ 2023, and I'm continuing to work on the WG23, which is about safety guidelines, and especially the safety guidelines for C++ group, as you can think. When Jens asked me for the keynote, and I thought about what to talk about. Actually, he told me, well, Peter, pay attention. Don't become the ranting old man, or the grumpy old man ranting. And unfortunately, I cannot hold myself back. I'm at my age. I'm almost 60, so it's kind of, you try to get wisdom, so you will actually end up doing some grumpy things. But nevertheless, I'm also an eager teacher. I love teaching. I started teaching in 1987 as a professional, while still a university student, teaching programming to others. I have done that on and off for most of my career. I was also doing software engineering research, creating stuff like platforms for internet banking in Switzerland, which was kind of interesting, was after I moved to Switzerland. I was a professor for computer science for 15 years, so it's kind of interesting. But becoming older, you end up with a situation that sometimes you just forget things. And there's the loss of memory, loss of recallability. You know that you know it, but you don't know the word for it. Or you know that person, but what's his name or her name? That's kind of stuff that I have. And looking up what amnesia means in the Wiki dictionary, or I think that's where I got that dictionary. And you see, okay, there's also a dope that's called like that. That's very strong. Not my flavor of a thing that I do. The strongest things might be a beer and maybe a schnapps, yeah. Now, related to amnesia, if you are old, you think the past was better. Who remembers code running like that in the blue box? Yeah. some exercise, yes. It's being sentimental. I would say I'm glad that I no longer have to use C++ 98 or even the C++ of the 90s when the compilers didn't have templates yet. No, I'm glad that we go into the future, that we have a bright future. So it's not only about the old stuff being better. But what I observed is that we forget the good parts of the old stuff to apply them in the modern context. And that's more or less what this is all about. I observed well-known knowledge that, let's say, my generation might have considered well-known is not applied or not even taught. Proven practices are not as well-known as I thought. Even after, let's say, 25 years, it's still not common practice. That's something that has proven to be actually very good. And again, scientific evidence is ignored, which is kind of a real problem today with a lot of things. I give some examples later. And we have timeless principles that get forgotten. I ask myself, why? And again, something that I'm guilty of myself, so in German you say, hold your own nose, that complicated stuff is favored over simplicity. And that's something that's quite typical for our profession or generally the trade of an engineer. I learn something new, I love learning something new, but once I learned it, I want to apply it. Now, the something new might be so complicated, so the most complicated thing is actually the most attractive thing to apply. And that is not always the best solution for the problem at hand. When I was teaching in 1988 a C training in Singapore, that was one of my highlights in my early career, I had one of the participants fresh out of university. The first thing, I know C well, the first thing he did, implemented doubly linked list. Who has implemented a doubly linked list in their life? Who is still using doubly linked lists? Especially the one that they implemented. It's one of the worst data structures. Why is it there that every CS student gets to implement doubly linked lists? It's there to form a humble worldview of the complexity of software. Nothing else. Especially with today's hardware, the benefits that we might have had of actually the extendability, the dynamics of a doubly linked list in the 80s, when I went to university, is no longer there. It's the worst data structure that you can have to have a sequential representation. There are very, very few tiny corner cases where it might be slightly better than a standard vector. Just use vector. Now, the problem is, what have we forgotten? Some examples what I like you to remember or made aware that collectively as a profession, as C++ programmers, as software engineers, we might have forgotten that. And it's completely unordered, so don't blame me, oh, it's not ordered by date or whatever, just arbitrary. Now, one thing I see that people forget about, there is Dave Parnas wrote a paper in 1972 on the criteria used in decomposing system into modules. That is a seminal paper. And he concludes the paper with several things that are kind of still true. Modularization fosters independent development. We have kind of boundaries that allow us to work independently and then mechanisms to glue the stuff together in the end. It gives us changeability because once we have an interface that is programmed against, we can change the implementation without having to redo everything. In addition, we can change the usage of a module without having to change the module, which is also changeability. Comprehensibility. A smaller thing is much easier to comprehend than a whole thing at once. And comprehension can also be built incrementally by comprehending individual pieces and then comprehending the combination, which is also something that's really important in software. Otherwise, it's unbearable. It allows us to high design decision, what brought us to abstract data types. Who has learned about abstract data types in their education? Okay. Who has implemented abstract data types in C? Okay, so you know what you do. But abstract data types in C is kind of a crutch for a crippled version of what we get with classes and types in C++ today. So it's not really that much difference. Separation of concerns is kind of, okay, separate the different parts of a problem into different modules. Not have the one magic class that does everything, or the one magic function that does everything. Or a main function that is 1,000 lines or longer. Who has seen main functions with more than 1,000 lines? You see, we all have forgotten about that separation of concerns thing. And there are other things about big main functions. The main function is the one function you cannot write a unit test for. And reassembly of modules, reuse. When I was at Siemens in the 90s, reuse by using object-oriented techniques was a big, highly funded EU project that I participated in. It led to nowhere, in my opinion, but nevertheless, reuse was then the holy grail to sell people, oh, use object-oriented technologies. We now reuse a lot, maybe even too much. Anybody heard about the NPM disaster where one module was pulled and then half of the internet applications didn't work anymore because of dependencies? That's something I talk about later. Another thing that's quite old are type systems. Alonzo Church invented the notion of a type system for his lambda calculus and published in 1940. So that was well before I was born. Now, type systems are taught usually quite badly. And one of the reasons is that you have these kind of very interesting formulas. Who has seen formulas like that in their education? A few. Okay, the problem there is mathematicians are very bad with naming. And mapping everything is by convention, and because they like very short formulas, they end up with having single letters just from different alphabets. It's completely, and you have to understand the convention of the current textbook or the current mathematician, what letters are used for what. And even though these formulas, once you grasp them, aren't that complicated, mapping those to what you get in a programming language typically is too much for a typical student or even an educator explaining that. So that got into the way of type systems, but actually type systems are really important, and I talk a lot about that a little bit more. Now, there are other things. In the 19th century, it was discovered that putting carbon dioxide, or carbonate is the word, but CO2 into the atmosphere actually leads to heating up the planet. That's not news. It's not invention from last year or the green parties around the world. No, it's just a fact that was discovered long, long ago and more or less hidden from the public for whatever reasons I don't want to comment right now. Unit testing. Who is writing unit tests for all their C++ code today? All. Who has written unit tests in the past for some of their C++ code? Who has never written a unit test? Confess.
All my code is in main.
It's something that was done very early on, even when there weren't actually great computers around. But Kent Beck published Smalltalk as unit testing framework for Smalltalk as unit in around 1989. I couldn't find the exact date. I should have asked him, but I forgot. And Eric Gamma and Kent Beck actually created JUnit on a plane trip, I think, from Zurich to the US for the Uppsala conference, or on the way back. I'm not sure which way it went, maybe on both directions, if they traveled the same way then. And I learned, went to a talk by Eric Gamma on JUnit, and I said, we need to do that for our C++ code as well. Actually, when I came to Switzerland, I took over the job that Eric Gamma left in a small company. So I took over his code base, and there were then no unit tests for it. That was my major contribution as a boss of the team to say, we start providing test cases for that. It turned out not to be that super commercially successful because we got our maintenance contracts canceled by clients because they told us, well, your software just works. Really happened to me. Nevertheless, it was good. We were able to create software that was meant to run solve just the year 2K problem, released in 1999, to run about 2 or 3 years. That software was in production at least until it was allowed to vote, and I believe even as long as it would be allowed to drink in the US. C++ with unit tests, and maybe not as simple as it could have been, but simple enough to have that such a long shelf life. What you also need to consider, any code that you write today, if it's somehow useful, it will be used much longer as you ever intended. Remember that. Now, with unit testing comes refactoring. It's about improving the design of existing code in very tiny steps. That was kind of made, let's say, the initial work on that was on C++ by Bill Opdyke, and in parallel by Bill Griswold, I think for another, I forgot the language he was working on, I think a functional language. I'm not sure if it was Scheme or something like that. And that was early 90s. Bill Opdyke's PhD thesis was in 1992 on C++ refactoring. It was made popular by Martin Fowler's book in 1999 for Java, and he re-released the version of his book for JavaScript in 2018. Unfortunately, C++ is challenged by its syntax and its legacy. Building C++ refactoring tooling is much harder than for other languages because of the preprocessor, because of the, let's say, interesting syntax in some cases when you need to parse it, you need to know if an identifier is a type or something else to actually apply the correct grammar rules. And also, even though we have open source compilers, or even the source code of closed source compilers, it's very hard. A compiler will throw away a lot of things that you would need if you want to build a refactoring tool. Just consider what you see with Andreas Fertig's CPP Insights tool. That is what he renders, this tool renders on the right-hand side is some part of the internal representation of the program on the left-hand side. And it leaves out a lot of stuff or generates a lot of stuff. For example, a lambda, you get a class with the overloaded call operator. And building refactoring based on that syntax tree that contains the exploded lambda, which is a struct, is not what you want to pull back when you move the code around into your original source code. You still want to see that lambda. That is what makes C++ refactoring hard. The compilers don't have the corresponding syntax trees that are suitable for refactoring. You need your own parser, your own syntax representation, and building that for C++ is just very, very hard. Another thing people forget about is the danger of fascism and populism. We even have in Europe now governments who try to actually build camps for refugees to process their immigration as asking for asylum. That's not really nice. And we might see even more on that. And remember what happened to fascism from this, actually starting more or less from this city. That's not what we want to repeat. My parents both lived through World War II, maybe on the wrong side, but they were born into that. And they never talked about the trauma that they must have suffered during that war. And I don't want to suffer a similar trauma because of wars. And we have them now in Europe and around the world. And climate change actually will make it even more problematic. Oh, back to software. Software architecture and patterns. Who has read at least one design or pattern book that has pattern in its title? Okay. Who has read more than one pattern book? Okay. Unfortunately, when people get taught design patterns, very often people get just the first design patterns book out of the shelf, and that is taught, the 23 Gang of 4 patterns. Is that true? Who has been taught the first exposure to patterns was not the 23 patterns of Gang of 4? Okay, a few. Who has the first exposure to patterns were the 23 Gang of 4 patterns? The majority, okay. Software patterns started around at least 35 years ago. The Gang of 4 book is 30 years old now. Ours will be 30 next year. And if I look at the curricula on where there's architecture in computer science or in software engineering, well, it's always taught with respect to cloud and distributed systems and whatever, and it's always about complexity and not about reducing complexity. Also, what's often neglected when teaching people, oh yeah, do that linked list, but nobody cares how that code looks like. Just that it somehow seems to work. And maybe the typical bugs are detected by test cases. But internal software quality, even if we cannot measure it, is something that is often neglected, sometimes deliberately, when it's about good enough software. No, that's never good enough. And also because especially managers not having built software don't get the quality that, let's say, lower quality is more expensive thing with software. If you build, let's say, a table like here, and you make the table 2 millimeters thinner, the table parts, it still looks like a table. It might even function perfectly. It might not hold the load of a back of an elephant, but maybe the back of you, so it's still okay as a table. So, but with software, if you make the quality worse, it gets more expensive because you will have more bugs, you will spend more time debugging, and any kind of debugging tools, even the great ones that were shown here at the exhibition, will not help you with bad quality. It's only to maybe improve it afterwards, and you want to build it in. All that leads to good software principles that have been forgotten. And the most dominating one that's often forgotten is simplicity. And that doesn't mean simplistic code or only using primitives. No, it's about making the code simple and elegant. And I know that my friend Kevin Henney is talking a lot about that, and myself, I try to foster that for more than a decade, and it's still not there yet. Whenever I see a piece of code, I say, huh? Yeah, I would have done that slightly different. Could that work? Maybe. Separation of concerns. These 1,000-line functions, even the 100-line function, is much too much in there. Too many things at once. And actually, interactive debugging leads to gives us a force to make longer functions, because then I don't lose context where I'm in. I can step through and maybe even step backwards. But that's not what separation of concerns is about. It's completely untestable. A 100-line function might be completely non-unit testable well enough. High cohesion, put things that belong together and separate the things that don't belong together. Loose coupling. Coupling is important, otherwise we have pieces that fall apart, but you want to be able to change it. Think of Lego bricks. You can put them together, you can put them apart, and you can inspect them individually. And that is what your software should be about. Not that you pull at one thing and you get the whole source code at once, have to compile everything. I was talking with someone during this week, oh yeah, we want to write tests. Yeah, but the link times are so long. Well, the unit test, if I take one component, I get the rest of the system. I cannot separate it from it. And that's not that nice. You want to have looser coupling. And if you think you have loose coupling, try to make it looser. Exchangeability is another thing. You need to change things. Software lives long. Some things might just move away without you knowing. And if you rely on them fixed throughout your code base, it will become a shotgun surgery, which is another code smell, where you have to change the code everywhere to actually fix it. So you stitch in a lot of places, and that is also highly risky then. And testability. Fortunately, testability, working towards better testable code, actually fosters separation, looser coupling, and high cohesion. So these things go together in a virtuous circle. But who's doing that? Not everybody was raising their hand. I do all unit tests in that talk. So that's half of my ranting done. Now the question that I ask myself, what are the reasons that things are so bad? At least from my perspective. And that means I speculate. This is completely unscientific. So it's just, maybe it's for fun. I think it's more than just fun that I'm taking that. But I have some hypotheses, and you might actually go out there and do research if that's really true, or you might just laugh it off as a good joke. I don't care. It's just I have some things I'd like to, as my grumpy old self, rant about. One reason that I observed, having written programs on, let's say, 8-bit computers with 48 kilobytes of RAM, which was actually one of the biggest that you could get, at least afford from my the money that I had as a kid, or let's say a teenager. And one thing that I observed is, well, hardware advances are guilty of getting bad software. Just consider the phone that you have in your pocket or in front of you is about 100,000 times more powerful than a Cray one, the supercomputer at the time when I went to university. I hope I got the number right, but I think so. And so hardware got faster over the years. Today we got more hardware because you cannot go faster because of physics. There are some limits. I even learned about physics limits. I asked, why don't we have 8K TVs yet? And then I was told, well, you can't see the difference between 4K and 8K, at least not on a regular setting in your living room. That might be the case. Now, what happens? I observed companies fostering things like CORBA, Common Object Request Broker. Who remembers that? Oh, old enough people. We had RPC well before, and it worked. We had protocols that were speaking plain text on socket like HTTP that worked well, but then we got the strongly typed Common Object Request Broker architecture, and that was a misery. It was highly complicated. It required architects writing generators for others to write code, and people became completely unaware about the remote situation when you made a call. I've seen more than one project fail because of that remoteness was so horrendously slow that the systems actually could never work reasonably. When you get the granularity of remote things too fine granular, the latency of the network kills your system. I'm not exactly quite sure about Java, but I think Java was fostered by IBM and Sun to sell more servers. And consider, it was a language built for simplicity in the beginnings. It was nothing really new. It stole syntax from C++ and the P machine from USD Pascal, for those of you who remember. And added some extra statements for the object management, but it's kind of P code with some extra is what the VM of Java did. XML, it's one of the worst syntaxes for data representation. Who has used XML? Who's still using it? Fewer, okay. Let's say the claim was, oh, it's human readable. Who has ever read an XML file as a human? Who loved it? No one, okay. It's really big overhead, it's hard, expensive to parse, and at least we got JSON now that is at least more popular for a lot of things. It has also its drawbacks, but actually consider XML required us to provide a schema, and that's actually a programming language or a language grammar. Who is a programming language expert in this room? A few should actually raise their hands. And compiler experts know how hard it is to get a good grammar for a language. Now consider everybody that uses, or let's say specifies an XML schema had to become a programming language design expert to actually make it worthwhile. And that didn't happen. I'm stopped talking about EJB, same story as with Java, but then we have blockchain and cryptocurrencies. I hope nobody of you is invested in that scam cryptocurrency. We have cloud. We have cloud computing. Yeah, distribution. Remember, latency. VR, that is not, there might be useful applications, but AI, that's the snake oil of today. Like Corba, like everybody, oh, we need a Corba strategy. Now everybody has to have or we have to have a blockchain strategy. Now everybody has to have an AI strategy without actually understanding what it's for. There are niche applications where it might be useful, but in general, having statistics run the world is not really a good thing to do. Branding. Again, holding my own nose, the nerd and learning culture we're in. Who considers themselves or herself a nerd? Okay. Why are we nerds? We like to learn new stuff. And that typically makes us good people in technology. The problem is there's always more new stuff to learn, so we might lose interest in the old stuff. It gets forgotten, or it gets no longer popularized. And if you look at the majority of the people who are not actually here that program in C++, they lack the ability either to learn that quickly, the motivation to learn that quickly, or the environment to be able to learn that quickly. And they suffer a much longer learning curve than those who consider themselves a nerd. First, they haven't learned that much yet. Maybe they're just too young to have learned that much. And they might not have the environment that fosters learning. So they repeat all mistakes again. Why did I think that is important? I'm also regularly speaking at an embedded conference, an embedded software engineering congress in Sindelfingen. And when I first went there, the end of the North, maybe 2009, 2008-ish, and I came there, well, for them, object orientation was a big new thing on the block, and C++. Well, I was going to object orientation programming languages conference in the 90s, speaking there. So for me, OO, that was a done deal. I already moved away from OO because it created too many problems because of dependencies. But for them, it was just the fresh new thing. So where they were 10, 15 years backwards oriented. And I observed over the years, they make the same learning curve, sometimes even slower, because it's not the main domain, not the main problem. They don't study programming languages. They want to create solutions for stuff that runs the world. It's really a thing. Same mistakes are made again. And that's really makes me sad sometimes. Another thing, conferences, books, media often have to sell new stuff. And we might not even be able to invent new stuff as fast as they'd like us to. So we sell old wine and new skins and get drunk from that. And it's really a problem. The old stuff gets too little attention. The proven stuff doesn't get enough attention. And that is really a reason for we forget about them. Oh, it's no longer in the news. Well, there might be actual reasonable application for the Corba architecture. Who cares about that today? No one. It was the hot thing in the 90s. Everybody had it. Another problem is powerful men, and I deliberately used the male gender here. They're drunk by power and money. They want to control the world. unfortunately also hoard money, and money buys the world today. And I observe them, we all observe them, they lack social responsibility. And that slide was made before we had last week's elections. And the big problem is too few benefit from the most. And that's really something I regret from reliving the 80s or even the 90s when Reaganomics, Thatcherism, neoliberalism came up on the political agenda. Everybody was following that, and now we're suffering from the results worldwide. The markets don't solve the world's problem. They solve the wealthy people problem. Being a teacher, and especially having taught at the university level, education is hard. It's often badly paid. I was lucky that I was teaching in Switzerland, where, let's say, educator salaries are a bit more reasonable, especially compared to the experience that you need with respect to Germany and other countries. Italy, for example. And it's actually expensive to prepare a good coursework. It's really expensive. Some people who give talks, not, but actually university coursework might even be harder to prepare because you might need to spread it out across several people to teach the same things, which I try to avoid, but which has to happen in some domains. Sometimes, to counterbalance that, universities try to get very stable curricula. The problem is, once you need to talk about something related to technology, the world changes so fast, so if you base something on a technology, you teach obsolete techniques. And it requires a lot of effort by the teacher and self-motivation to actually keep up to date with that. And that's not actually paid for. Then there's the other thing that, we need to follow market demand. The problem is when you set the market demand when the student starts, after 4 years or 3 years or 5 years, the market demand might have changed. We get the new kid on the block and the news to actually work for. I trained on CORBA in 1999. Well, I'm finished in 2004. Now everything is Java. Who cares about CORBA anymore? And also, because we have to focus on technology, the fundamentals are not well understood. I learned that I got taught sorting and sorting algorithms because sorting algorithms have a spread of different implementations that differ in their analyzability on complexity and give us a treatment on how to actually judge the complexity of an algorithm. That's what, by sorting, is an example that everybody learns about at CS Education. Who has done sorting algorithms? Almost everybody. And that is something, who implemented a sorting algorithm for earnest in production? Very, very few. So you don't need sorting as, implementing sorting algorithm as a professional feature. The market wouldn't demand it. But you need to understand how to analyze complexity of algorithms. And that is something you need to be judgeful about, to actually, sometimes things are taught not for making the same thing at home, taking it with you, like doubly linked list, like sorting. Sometimes it's taught to teach you some underlying fundamental things. Without understanding pointers, we couldn't be able to get HANA's greatest data structure, which I forgot the name about. Without understanding pointers, we wouldn't be able to understand the data structure. But it's something completely different from a linked list, and it might be worthwhile to implement it. I hope we get something like that in the standard library so that I don't have to learn how to implement it. Experience takes time and practice. And again, practice is something important for programmers. It's a trait. We have to actually practice a trait to get better in it. We cannot learn programming from a book. We have to code. And that's something I regret at the moment. And it's kind of a two-edged sword. To practice, you need time to practice, but practice takes away time from learning other things, or takes away time from preparing new material for your students where you actually apply it, so that even extends the time for preparing education material. Back to the market demand and trends. Trends are something that kills sometimes our profession. It's not only the new stuff, it's just if everybody is doing it that way, maybe it's not that bad, so I just do it that way. I cannot get fired for doing it what everybody else is doing it. If you really want to apply something, think about the consequences. That's something I learned from writing patterns. Think about the bad consequences and the good consequences. And sometimes fighting the bad consequences or saying, no, we don't apply that technology or that thing because the bad consequences don't outweigh the good consequences, you have to swim upstream when everybody else is doing it. Now, when I was doing C++, let's say in the zeros, everybody told me nobody's doing C++ anymore. Now we get C++ conferences again because C++ is evolving and it's now news again. But the validity of good C++ code that has been written in the zeros, you might need to have the ability to make it simpler because we have better mechanisms in the language. But that is actually something to think about, that don't follow every trend. Think about the consequences of a trend. Just because it's popular doesn't mean it's good. So, think about the risk, but actually swim upstream if you know that downstream is the wrong way. Don't be ignorant of the consequences. Now, why are we following trend? Well, there's also, I observed, especially in politics, but even in other things, populism. Oh, someone points, oh, this is guilty. They are guilty. The witches are guilty. Remember, when they point this way with the index finger, they point 3 fingers to the real guilty person. Populists tend to have simplistic solutions that are loudly presented, but wrong. They won't work. And that even goes for software sometimes. If you get sold the next new programming language, think about the consequences. It might be too noisy, too loud, and wrong. I'm not saying every new programming language is wrong, but some turned out to be not as fanciful as the initial look at promised. Think about being calm, having realistic approach to solving the real problems and have actionable things instead of putting people in refugee camps and saying, oh, if we put them in a camp, we no longer see them, the problem goes away. It's like pushing out homeless people from the city just so that nobody sees them again. Give them a home, that solves the problem, instead of pushing them out of cities so that people don't see them. Now, actually, I have to listen to Jens and stop the ranting. Now, I'm a teacher, I'm an eager teacher. What can I help you to remember the things that might have been forgotten? And I have some missing ingredients I like to talk about a little bit, and excuse my alliterations, just the architectural abyss or the abstraction agony, automation of tests, and the abracadabra of simplifications. Now, what's with architecture? The biggest thing about architecture is managing dependencies. And dependencies sometimes are hidden without you seeing it. Being it, oh, I'm using a singleton. Yeah, that glues together all code using that singleton or that global variable. Remember, Kent, Beck, and Eric Gamma, they confessed singletons don't use singletons. They are global variables in disguise. One reason why C++ might have used singletons in the early years is the dynamic initialization of object with static storage duration. We have undefined sequencing of the initialization across translation units. And that is one reason why something like singleton was invented then or used in the 90s, when it wasn't even standardized. We had the problem if you had globals where initialization was interdependent, you want to make sure that the other global that you depend on is initialized when you need it. That's where it came singleton from. been there, done that, suffered from global initialization, dynamic initialization dependencies. Those are the programs that crashed before main even started. Just consider how you debug that when you cannot set a breakpoint on main. Okay, but do it differently. Just don't use globals, or at least not those that require dynamic initialization. And we've even got const in it in the language to solve that problem. Another thing that architecture is about, reduce duplication. There's a thing called don't repeat yourself. Dry code is one of the principles of clean code, I believe. Or sometimes it's called once and only once. It's just harder to pronounce than dry. Who has heard of dry code? Okay. Who is applying that for all their code? Consciously, subconsciously. Actually, that is something you should do you should be so ingrained that you should do it subconsciously. Whenever you see a code duplication, you should get the gut feeling, oh, something needs to change. Sometimes it's developer laziness. Most of the time it's ignorance. They just don't know how to do better. I assume usually developers try the very best they can, and they might learn afterwards how to do better. So it's important to lose the shyness to refactor existing code. Make it simpler when it can be. What else is in software architecture? Well, I can cite my own book, so I do that. Software architecture is a description of subsystems and components of a software system and the relationships between them. So it's about parts and the things that go between the parts. And there are several perspectives you can have to that, how you arrange your files, where to put them in the file system for the build, how you place the functionality across processes and threads. There's logical things that are often underappreciated, like layering, and there are physical things like mapping stuff to hardware, especially in a distributed system, you need to know where things go. And if you look at what is a relationship, relationships are the hard parts. Those give us the dependencies, and sometimes they are hidden. And the hidden relationships are the hardest one to deal with because they are not obvious. There might be timing relationships. Oh, that bug only happens on the production machine that is a bit faster than my local PC. That's a typical thing where you have a hidden relationship in timing about several things that just don't happen in the same order on different machines. And if that happens, you might have a data race, which is undefined behavior anyway, so you get what you deserve. Or you might have something else by design, which is just a regular race condition, which is something you didn't care about. And those happens even in real life. And the important thing is actually be conscious about the relationship and minimize and loosen the coupling. That is the important thing to allow testability, exchangeability, and a lot of good quality attributes of software that we also learned this week about. Patterns for software architecture. I don't want to read that out, but the important thing is actually that patterns descriptions, no, that's the wrong screen. There we are. Is the consequences part. That is where the POSA books are a bit different from the Gang of Four book. The consequences in the POSA books are about benefits and liabilities. So the bad parts of applying a pattern are also described. And those, when I read a pattern, a new one, I'll first look for, okay, that's the context of the problem. And then I look for the liabilities because that gives me an indication if I should actually apply it or continue reading it if it's applicable in my situation. And those liabilities, all design is about trade-offs. And patterns are about design and it's about trade-offs. Be aware of the trade-offs of your design decisions. If you only know one way to design something, that is a limiting facility because you have no means to actually honestly consider the liabilities because you don't have an alternative how to solve it. That having too many alternatives also is a problem because that gives us such a broad spectrum, we might be unable to judge all the liabilities that we get from all the variations. That's where patterns actually help. And one important pattern that I'd like to share with you just as an example is the layers pattern from our book. And the layers pattern helps structure applications that can be decomposed into groups of subtasks, which each group of subtasks is at a particular level of abstraction. And the important thing is that level of abstraction. Where are we? That is actually the important thing, the levels of abstraction. And dependencies from a higher level of abstraction go always to the lower level of abstraction, not vice versa. And that gives us exchangeability of layers. Anybody has written portable software? You rely on that abstraction layer that you put underneath your system so that you can change the operating system across that. That is one application of the layers principle. You have the exchangeability of layers, but that's also on top of that. Who has written application for multiple applications for the same system with the same frameworks? Again, that's layers. You have used the same abstraction to write multiple things, so you have the exchangeability of the upper layer to get different applications. But if you look at the liabilities of that pattern, it's really difficult to establish the correct granularity and the right level of abstraction when you're creating these layers. So it's not easy to come up, oh, these are our layers, now we filled it in. I've seen systems where prematurely, oh, these are our layers, and then people couldn't figure out, yeah, what is the actual abstraction of that layer? So they programmed kind of in every layer the same functionalities, the same API with different namings, maybe different types, but still doing the same thing. That's not layering, that's just busy work. Just to show you how hard it is, the diagram from our book, the red arrows are I added for this talk, is, okay, yeah, it's very generic. How do I know that component 2.1 is actually at the same level of abstraction as component 2.2 and a higher level of abstraction than component 1.1? It's just hard, as hard to get up a diagram like that. Now, who has programmed something where you had a database layer, business layer, and a UI layer? Okay, maybe a third, a bit more. Now, that's actually a multi-tier application, and tiers aren't layers. And this is where our book is kind of wrongish, because we merged them together. In a tiered system, a change in the application is not only in the top layer. It usually crosses all the tiers. If you, let's say, extend, oh, I forgot, let's say, now I need to have the address, the house number differently from the street name, and I need to change my database schema, I need to change my business logic because it's a new data member in the class, and now we have also the UI where I have a separate field now for the actual number of the house. And that is a typical thing where a multi-tiered system changes in logic are not encapsulated per layer, but across the tiers. On the other hand, the technology abstraction of a database layer, yes, you can exchange the database, exchange Oracle and pull in whatever other database you might need. That is something possible, but it doesn't give you that level of abstraction that the different layered system actually provides you with. Now we talked about architecture. Who has architect on their business card or job description or whatever? Oh, very few. Okay. Now I've worked with teams, or let's say observed teams, where they had a so-called capital architect. Sometimes in disguise as a scrum master or whatever architect, saying how things are done. We had the example of the Mythical Man Month in Titus' keynote on the top surgeon doing all the things. Actually, a top surgeon doesn't do the operation. It just supervises the others most of the time. Unless something really bad happened, then they might jump in. But beware of the architects. There's actually a pattern from a pattern book called Organizational Patterns of Agile Software Development by Jim Coplien, who might be known to some people in the C++ world around from his, what's his book name? It's too old, I forgot the title. Huh? Say it again? No, the very first one in the 90s. I forgot the name of the book. Nevertheless, but organizational pattern is much more important, just much more forgotten. And one pattern there is architect also implements. I've seen that a version of that pattern that was called architect always implements. So whenever you, in your job, are meeting with such a capital A architect and you have a gut feeling, maybe that's not right what they are actually telling me, ask why and where is your code? And if that doesn't give you good answers, maybe if you can change your organization, change your organization. Another pattern. Now, I told you layers, the level of abstraction are hard to get right. Now, what is actually abstraction? It wasn't explained to me well, so I need to come up with my own definition. What is abstraction? And the key thing of abstraction is actually give a name for stuff, whatever stuff is. And recall the stuff by using that name. I use the name layers, and you get an intuitive understanding because you might have accumulated some stuff behind that name layers. And that recall via name, that is what's abstraction. That is actually what makes our profession so powerful. We are able to deal with multiple levels of abstraction at once. And our tools, programming language, allow us to express abstractions and recall them at will by using the corresponding names. So we can invent our own magic spells and recall them and cast them. That is the power of abstraction. We hide the details behind the name. We don't have to use, let's say, dip switches to flip the bits to get something done. No, it's there. We write software, we call print, and it prints something. And we don't care how the characters are rendered on the screen. We just care that it does what we expect it to do. And there's a whole bunch of stuff going on underneath, and I don't go into any details about using Unicode or so. That's a different topic for other people. That's something I try to shy away from. And that encapsulation enables us to change things. If something's wrong, we can implement a different print or provide a different print implementation, and it's still doing something better without having to change the usage. So it gives us ignorance what's behind the abstraction, and also the abstraction implementation can be ignorant about its usage. And that's kind of a very important boundary that we get from abstraction. And that is something that's completely underappreciated, to having those boundaries. Now, once we are using those abstraction, once we recall something with a name, we can actually add parameters to that thing. So we can provide different arguments in different recall situations, getting slightly variation in behavior or in what the meaning of an abstraction is. So we get the power by providing abstraction, we get the power of flexibility. Also something easily forgotten about, oh yeah, we have parameters. No, we don't have to just call a piece of code. No, we can actually make it adaptable to current new situations and let it work differently and be more generic. I'm writing it only once and using it in many different times. And sometimes the more generic solution can actually be the simpler way to actually get it. And if you look at what can we abstract in C++, there's a whole bunch. C++ is especially strong in all the levels of abstraction that we can actually do. We can abstract from a value and expression by putting it in a variable, having a name for that expression. A computation sequence, we can put in a function and have a name of that function to call it. And we can even parameterize it with different arguments. So different arguments give different results of the same computation. We have if you have an operation that is kind of generic but differs in some parts for different types, for example, we can use overloading. We might have a set of functions that behave similarly for different types. We can use a function template when the body is actually identical. We can have a set of values and behavior which forms a class type. We might have a set of types that are very similar in behavior, especially from the usage part, and we can put it in a class template to get more flexibility. And there's other related stuff that we put together, especially functions together with the types for ADL, and we put it in a namespace. That's all the thing that we can name. The only bad thing, namespaces, we cannot parameterize yet. How do we provide parameters and arguments? Curly braces, round parentheses, and angle brackets. Oh, not angle. How do you say this? Huh? Chevron, yeah. Well, a chevron is usually with two, but getting these triangular things, and some people shy away from, oh yeah, that's a template. Oh no, templates, no. Who's shying away from templates? Not the people here, but I'm sure at home you have friends who shy away from templates. No, they aren't that pointy. Just squeeze your eyes a little bit, or just getting older, you no longer see that sharp, so the pointy end is not that bad. It's just a parameter or an argument that you provide. And with templates, it's even beneficial. Very often, the arguments are deduced for you, so you don't even have to spell out the arguments the arguments through the template itself, because they are deduced from context. So we have arguments provisioning at compile time with all three sets of parentheses, and at runtime we don't have the angle brackets, so they don't hit you at runtime, which is also a good thing. Anything at compile time, if it's wrong, you get told so. At runtime, your users tell you, which is a bit later. And I don't go into details what you can do with parameterization. What are the strengths of C++? C++ has the powerful abstraction mechanism. We have compile time type safety, and a bit more on type system and type safety in a moment, and it generates efficient code. We don't have a virtual machine necessarily underneath it. That then gets repatched with just-in-time compilation. On the other hand, it cares much about backward compatibility, which is a blessing and a curse. Just say ABI. And the last point is also responsible for some of C++ weaknesses that I don't want to, that I actually eliminated from this slide to not worry more. But you should actually stop worrying and love the C++ type system. And there are actually, that the C++ type system is a strong type system is by design intent of Bjarne. We should love him for that. And he says, okay, type errors are always reflected either in a silly programming error or a conceptual flaw in the design. So that a corollary of that, any typecast that you write means you either have a silly error or a conceptual flaw in the design. A few corner cases are exempt, but I don't go into those details yet. Now, what is a type? From theory, I learned a type is actually a set of values and a set of operations. So these curly braces are the mathematical thing. And the operations define what you can do with the values. So the operations have parameters of the corresponding type, and they get arguments which are values of the type and maybe produce results that are values of that type. So the type provides actually what you can do with the values of the elements in the type. And as Bjarne said, types provide meaning to program. And now once we have a type and many types, we get a type system. So we get type system defines the meaning of a program. It tells the computer, or at least the programmer, how to interpret the bits of some data bits. And we learned about type punning yesterday by Jonathan. That's kind of almost undefined behavior in almost all cases. And that's actually a good thing, because misinterpretation of the data bits actually is something that is a wrong program. And we want to prevent wrong programs. And better let the compiler prevent wrong programs than the user tell you your program is wrong, because then you have to spend a lot of time debugging. So raising the type error should be raised by the compiler if your program is meaningless or silly or ridiculous. And that is the important power of type system, and that's really underappreciated. Over the last decade, I've given talks, I've seen talks, many people have given talks, written frameworks on strong typing? Who is consciously using strong types instead of in, string, or whatever in their design? Who's never heard of strong typing? Think about strong types telling you getting rid of ridiculous bugs. Invest in strong types. Use whatever system you're using. Watch talks by whoever you like to, and use the frameworks whoever you like to. I have my own. We have Jonathan's. We have. I forgot all the names. Just look out for that. Now, what are the benefits of the C++ type system? It detects type errors. The problem is it supports implicit conversion. That can sometimes be very handy, but most of the time it really gives us a lot of ugliness. So make your constructors explicit. Just one example. Be aware of the implicit conversion of all the built-in types. That's what Misra tries to care about a lot, and we fail to get a good enough set of rules about that because it's just too complicated. And sometimes it's really convenient to have implicit conversion. When I started my programming career, I was taught Pascal, and yeah, you couldn't actually mix real and integer, actually, not integer. And that was kind of annoying, especially when you learn C and then everything just works somehow. But that's actually a curse. If everything just works, like in Python, you hit just later at runtime with the bugs or type errors. Type deduction is actually one of the magics why I love C++ for. And just appreciate auto and templates and type deduction. Learn about overload selection. It might be non-intuitive, but it's actually the powerful way of writing simpler code because you write the code once and use it for many situations. Template instantiation, yeah, Svinaya concepts, yeah, can be complicated. Just try the simple version without considering concepts. Especially don't over-constrain your templates with concepts without need, because that actually takes away one of the big benefits, especially from class templates, where instantiating a class template is possible, even if your arguments don't fulfill all of the parameters concept. If you're not using the non-fitting part of the class, that's still valid code until you actually hit that non-fitting part. And the type system is static except when dynamic, and that's virtual and dynamic cast. And I suggest that you refrain from making everything dynamically typed, regardless of what language. And in C++, it gives us, when I teach C++ today, I teach people virtual very, very late in my courses. And I also teach them how to encapsulate it with type erasure, just to show them, hide it. Values are the important thing. I'm not going into that talk, but just remember, value types are much easier to work with, to argue with, to put on, get your little Dijkstra consciousness to prove actually that your code is doing what it's supposed to do. It's much easier to do that with value types. I skip over the weaknesses. I talked about that. The important thing, get strong typing, use static analysis, compiler warnings, and follow guidelines to avoid the weaknesses and program away from them. The strengths I also talked about. Classes make a strong type system. Bjarne told us so. And if you just remember, not everything has to be a class. We now have enum class types, and those can actually be strong types for integer-like things. And if you want to get examples in the PDF that I provide, you get some links on how I try to implement integers that don't silently convert and don't have undefined behavior using enum class types. And I regret that byte has operators defined for it. It should have been only for memory. I didn't pay attention enough to prevent that. I'm sorry. I apologize. That's important. Apologize when you're sorry. And there are many things I would have to apologize for. It's just too much happening in standardization, and I'm not going next week to Wrocław. because it's just too much for me at the moment. Now, the last thing I'd like to talk about is testing. In my opinion, interactive debugging, sorry for those from Andu, even with the best tools, is the greatest time waster ever in software engineering. I personally haven't used an interactive debugger for C++ for decades. Not for other languages, yes, especially Java, but not for C++ code, because I write tests for my code. Whenever I have a mysterious behavior, I write tests for that behavior to check if it's really that behavior. A debugger might or might not tell me, and it's much faster for me to write a test case. Well, I might not have those big intertwined code bases where writing a single test case has to compile everything, but that's also a corollary of writing tests first. So test-driven development also gives me or anybody immediate feedback on design decisions. Whenever you intend to write a test and a function turns out, well, that's quite hard to test, the test gets complicated, or the tests are complicated, I need too many of them, that's an indication that the function has no longer high cohesion, is doing too many things, and might need to be split so that the test gets simpler. So the most important thing that you should take home, have guts. Good unit tests. And actually, my friend Kevin Henney is giving a talk on is giving a training on that next week. So if you want to learn about guts, book that, or call me. I have a little bit more extended training on unit testing. Call me, I'll show you how to do that. And I usually look at the code of my clients to see how they're faring and get ideas what I need to teach them deliberately. The important thing about the test-driven development cycle, actually, it's a circle. It's you start with the test, you write a piece of code making the test compile and run, and then you refactor. And that blue part, let's see if I can get that, that is important. Don't forget that refactor part. That is a real hard thing. Make things simple. Simplify the design. And also, everything is really, really tiny steps. If you think, I have to walk that way. If you think that step is tiny, no, it's like that. And maybe even like that. Those are the steps that you take when you write tests in TDD fashion. It's not the big strides, but making these tiny steps and following that circle maybe twice in a minute is actually what makes you, giving you sustainable speed. You never get in a situation where the code is so broken that you have to debug it. And if you want to learn more how to get there, that's a full training, not today. I skipped those rules. Now, why refactoring? Refactor. Change the code to become simpler. There are a few refactorings supported by IDEs. Not all of them are actually there. Rename, at least, is supported everywhere. And you will end up with learning about your code and think, oh, that name is crappy, we need to rename it. Unfortunately, we cannot do that with a standard library. So once you release something to the world, the names are fixed. That is where writing tests for your code, also you suffer from your design decisions, but you also are able, while you haven't released it, to keep to make the names good enough so that they actually say what they are doing. If a function gets big, extract function is something to apply. And it's also something, if you have existing code, extract function, if you have a long function, let's say 20 lines, it might actually hide 3 functions in it, extract those 3 functions. Each individually is much easier to test than the whole thing with 20 lines. And that's true even if it's 200 or 2,000 lines function. Extract the pieces that belong together and make them small and testable. Introduce parameter is something you would have to do then, and moving around, and especially in C++, replace loops with algorithms is a very good, powerful refactoring. Try it. Who is consciously using standard library algorithms? With loving loops. Who has people at home loving loops? there is potential for learning. And actually this week on social media, one of the agile people, J.B. Reinsberger, actually wrote, "Why refactor?" And there's a technical thing to reduce the volatility in the marginal cost of features. Yeah, that's kind of, how do you say that, cost? It's kind of economic speech. No, actually, it's to express love to your future self and to the people that have to use your code in the future. You show love for the job, for the code that you create, to make it simpler. And love your code base, make it simpler. Don't hate it. Hate is not productive. Love gives you the future. How can we simplify? The magic spell of code simplification. Refactoring is one of the mechanics to do that. And the overall thing is, less code is more software. That's a philosophy I borrowed from Kevin Henney, my friend, and we share that. We both had the idea of having something, or he said the idea of decremental development, reducing the code size to 10% while having a better design and preserving the functionality. Not by 10%, to 10%. And I've seen many code bases where it's even a bigger saving possible. Now that's overwhelming. Another old friend of mine, Ward Cunningham, the inventor of the WikiWeb, not Wikipedia, but the WikiWeb. And he worked together with Kent Beck, and whenever they got stuck, Ward would remind Kent about, well, do the simplest thing that could possibly work. And that philosophy helped me a lot. When you don't know what to do. And very often you see something, a complicated solution, and I try, if I would redo, what would be the simplest thing that could possibly work? And that is a philosophy that's also not well known, but it's a proven practice in software. And the elders seem to have gotten it. Do the simplest thing that could possibly work. Don't start with a complicated thing that just learned this week, next week. Look at your code, try what would be the simplest thing that could possibly work. It might not work, but then you haven't invested that much to actually, when it actually fails. Just one example. A couple of weeks ago, I was at a client, they're doing embedded development, freestanding, no operating system, nothing. And I got asked, well, we need something like extended function, but without dynamic storage. I was starting to explain, yeah, you could do type erasure with small object optimization. But then I think, what for? Why do you need that? Oh yeah, we have these interrupt service routines that we want. It's a table of pointers to void functions, yeah. But we want to support member functions and free functions, and all that needs to go in. Well, what have you to say? Well, they showed me about 1,000, I think maybe even 2,000 lines, but a lot of comment in there, so I don't want to blame them. But at least a few hundred lines of scaffolding, including macros for setting things and stuff like that. I actually they showed me their use cases, and actually they had free functions, a few of them, and classes that all had the same member function that needs to be called. Well, that was the end of the day. The next day, in the evening, I was thinking about that over dinner, and then I said at my computer, what would be the simplest thing that could possibly work? I turned on Compiler Explorer, and what actually I ended up with is something, okay, why not make it a function template that would fit when instantiated into that interrupt service table, and take an object or a function reference and just call it. It realized that there are classes that were handlers which have state actually would overload the call operator, and that allows, and they have other handler functions, and the end, they just could have used the interrupt service in the ISR table, either instantiated with a handler object or a handler function, and it just works. So 1,000 lines of scaffolding into 5 lines or 4 lines of template. Function template, and not much more. Everything is static there anyway in their concrete system, and passing a reference to an object with static storage duration, it's what they were doing anyway. It's just in disguise. So simplicity is possible, you just have to have the right idea. And getting that right idea, remember, do the simplest thing that could possibly work. I didn't know when I was streaming at my dinner, over my dinner, if that worked. So I need to type it in and see if it worked with Compile Explorer. And yet, yes, it worked. So I could share it with them. Let's conclude. Remember, be human and love. Hate is not an option. It doesn't get us forward. It only gets us into the abyss. Restrain the climate crisis. I have no idea how. Maybe don't invest too much into AI. Resist populism and fascism. And help others to understand that they are suffering from being dragged in by scams, con artists, populists. Teach your surroundings. Regardless of the political direction, populism will lead to fascism, will lead to all kinds of problems and war. And I don't want to have a war. And we already have too many wars on the world. Simplify your architecture. Disentangle the knots that you have in your architecture. Get rid of unnecessary dependencies. Make dependencies obvious, parameterize, separate concerns. That's really hard. It requires work, especially in a legacy system. But there are even books about that. Working Effectively with Legacy Code by Michael Feathers, 20-year-old book, or maybe almost 25 years old. Still relevant. Read the classics, whatever classic is. Figure out what books were written 20 years ago that still have a shelf life. We still sell that software architecture book. Not many, but we still sell it. I get about a few dozen euros every year on royalties. Refactor your code and rely on test automation. And act responsibly. That's it. Questions?
Hi, thank you for the inspirational talk. You mentioned that you haven't used interactive debuggers in decades. What do you think about using interactive debuggers in education?
I have an opinion on that, and I have seen when I was still professor, my electrical engineering department colleagues who taught software, they were using interactive debuggers in education. And I think that gives the wrong impression to the students, because they think, oh, if the professor is doing that, I have to do it as well. Interactive debugging is the wrong way to teach programming. Writing unit tests, providing unit tests, showing unit tests, even without explaining what unit testing is about, is what I would teach to freshmen.
And about showing how the sequence of a program runs?
No, that's not giving. You have to make the people. I might do that in a diagram, in an animation, but not with a debugger. I deliberately wouldn't show that tool to people. If they actually need debugging, that comes later, to give them at least what Andreas Zeller, for example, shows in his book, Why Programs Fail, how to use a scientific method to consciously debug, not just sit there and observe without a goal, but having a goal to figure out how it's done. But again, scientific method also work with writing a test case. So you have a hypothesis of why the program fails, and you write a test case exploring that hypothesis, and then you see if it works or not. So it's not even, the methodology doesn't even require a debugger to actually debug your program.
Thanks.
Hi, yeah, also thank you for the great talk. I have a question. When you spoke about simplicity and the idea to do the most simple thing that possibly works, I haven't met a person that would disagree with that, yet still we have discussions about what that means. Simple example, I have people that I work with that would say, okay, I have this 100-line function here that does 3 things already. The most simple thing to do what I want to do is to put a 4th thing there, add 20 lines more code, and tomorrow I add another 20 lines more code, and then you have a 140-line function. I would say, okay, let's abstract a few things and move it into separate functions. And he and me both would say, oh, well, what I want to do is more simple. So how would you handle that?
Remember I told you have guts. And actually, if you have a function, let's say with 3 ifs, you might need 8 test cases to cover a full path coverage. And if you add more ifs, you add exponentially more test cases. So I guess that function that you started from didn't have good unit tests yet. And I would start, okay, I want to add that new thing. Why don't we write a test case for that new thing first? And now see how maybe other parts in that function could be tested similarly to convince them to make that work.
Yeah, that test argument would work if that person would believe that unit tests are worth his time. So, but I guess that's another problem.
Let's say, if you have people that don't want to learn, those shouldn't be doing software. Because our profession enforces us to learn continuously throughout our lifetimes. And it deliberately fosters it. I would say that's true of all professions. My father worked towards the end of his career as a janitor in the company. And even he had to learn new things every week, how things change, new tools that were acquired for him, other things that he might no longer have been able to do because of the kind of aging body, doing differently. Learning is a lifelong experience, and you should actually encourage that. And if you have colleagues who don't learn, I think that requires some intensive talking to do. And otherwise, if you need someone from the outside because they wouldn't listen to you, I'm available. Maybe not that much, but I have done those things and explained to that. And it's I also learned myself, the prophet in their own country has no honor. So it's actually, you're not listened to when you are within the organization. You just have to tell someone outside of the organization what to tell your colleagues. That's a typical consulting job.
Thank you, Peter, for the great keynote. And there's now some online questions. Guillaume Dua asks, any advice for a trainer, private and companies, who struggle a lot with juniors' strong beliefs and the inertia we have in the academic, which often makes teachers to teach very deprecated content? Some fight dogmas and bring pragmatism into leader-manager mind.
Would you be able to show me to that, because I didn't get it?
So,
can I read it on your phone? Because then I'm able to understand.
Can I repeat the question?
Repeating might not help.
Okay.
I'm hearing impaired, so I'm sorry. And I need my glasses. Okay, any advice, private in companies, for a trainer who struggle with a lot of juniors' strong beliefs and the inertia we have in academic, which often makes teachers to teach very deprecated content, which I was talking about. Some fight dogmas and bring pragmatism into leaders' and managers' mind. That's a tough question. If it would have an easy answer, it wouldn't be a problem. I have a hard time. I struggled myself, and I actually had to quit the job when my values were violated too much by the new leadership, or let's say managership in the university. So I don't have a very good advice for that question. With a very concrete situation, I might be able to have some ideas, but not in general. It always depends. It's always a people's problem, which is another pattern, or something you learn from Secrets of Consulting, which is actually, I would say, a pattern book from the 70s. So it's really hard to fight inertia I can succeed because of my long experience and also my courage and stamina and, let's say, maybe some leadership abilities and maybe just some dominance abilities that I dominate others. So I'm guilty of being such a crowned man sometimes. So that's maybe not striving for the money and stuff like that. But it's really hard to solve a people problem because it's always a people problem. Love people. Love them. Show them how to do better, and maybe that helps. You cannot pull out the whip. Show the love. Work together. Actually, pair programming is something that works. Mob programming. Solving problems maybe just outside of the work context together to see, appreciate trust, build trust, and learn new things. Code katas, all kind of things. And there's more questions, I guess.
Yes, it's the same question Nico had before. I have colleagues, you have a relative large function, and they want to split it because they see at once what this function does. And if you split it in more parts, just give another name for this step, and then they have to go into these paths to see what this especially does. And if you do a unit test for every part, you still have to do a unit test for the complete function because it's a sequence of this.
Yes, but the complexity of the test of the complete part can rely on that the individual units are already tested, so you get fewer tests from smaller functions, even if they are combined. Just consider one function, one branch, 2 tests. If you have 4 of those functions, you have 8 tests. Now, if you have 4 ifs in your single function, you get 16 tests to get all.
Yes.
Just consider that. And so you still have complexity, but you can actually reduce the exponential growth of test cases by making smaller units.
But in my experience, I had a case that splitting this bigger function, testing the whole function didn't do that what it should, because yes, there are something missing in the clue code of these other functions.
I'm not saying you never make mistakes with test-driven development. I'm just saying it becomes easier and it requires practice. It's not like, oh, we do test-driven development from tomorrow on and you're perfect the day after. Yes. That's not happening. From my experience, when I had forced my students, when they do their semester project work, I relied on test automation. The first third of the semester, I had to step on their toes to actually make them write tests. I only considered code existing when they had tests for them, and they had to show them to me. The second third of the semester, they were proficient now with that, and they had some more theory before actually starting the project work. And some students actually in the last third of the semester did big changes to their solution because they were so, say, relying on the test cases that they were brave enough to actually make these big changes, redesigns, improving the design, because they knew the test cases would actually catch any bugs that they made. And that was a learning experience that they had. It requires, let's say, hand-holding, either a bit pushing, sometimes a bit pulling, and sometimes a bit caring for them, showing them love, that you care what they are actually doing. I wasn't the professor that gave an assignment and then checked in the end if the assignment result was something. I always cared for the students who actually made that happen. Again, that's a lot of personal investment, not really paid for, but I wanted them to learn.
Okay. Thank you.
And another online question. Dr. Florin Ion Chattes asks, thank you for your talk. We do not have architects in our projects anymore. we have the so-called Scrum Masters that replace the project manager or product manager. Do you agree? And if yes, please speak out about this reality.
So, sorry, I didn't get the last sentence. Do you agree?
So I think he's asking, like, what is your opinion on Scrum Masters and this modern take on
Well,
architect-
Agile is not about mastering others. The term Scrum Master has very strange connotations if you consider where the term master was used in the past. Let's say, actually, Scrum Master is kind of that we have Scrum Masters, and Scrum is so popular. From the Agile people that I worked with in the 90s that fostered Agile, Scrum was taken on and kind of made a money printing machine by Scrum certification. Mm-hmm. That was actually killing Agile. Agile is about collaboration, collective code ownership, working together and improving together. Not about being told what to do. Actually, but figuring out together what to do and working on what you love. And I have a strong opinion on Scrum. I'm not blaming those who actually make the training and so on because they are forced to, but it actually killed the underlying values of Agile. Just look at the Agile manifesto and read what's written there. Most of the Scrum people don't follow that.
Hi, thank you very much for the great keynote here. And I've got a question about the strong typing. So I'm glad that you brought that up because I'm a big fan of strong typing, and I'm also looking forward for the quantities library, which will do us here a good favor. I have a question with respect to enum class in this respect, because I stayed away from using this kind of abstraction to express strong types because it feels wrong to use an enumeration for actually expressing a strong type. So I have been confronted with this. I stayed away from that. Now I have seen it here, so I wanted to know your opinion on that.
Actually, I gave a talk on. Did I give a talk? Yeah, I gave a talk on somewhere during lockdown, an online talk. So the video is online where I introduced my first iteration of that library, and you can see my code on GitHub where I provide different strong. Let's say I wouldn't say strong type. It's integer replacement types, but you could use the same idea to make it a strong type with operator overloading. I also have a strong typing framework, again with the idea what is the simplest thing that could possibly work, which is different from others. And the idea of a strong type is that you limit the amount of operations that are available. That's why I hate that standard byte got these bit operations. Byte should have been used for memory buffers only, and that's how I teach it. I don't teach the bit operations. So that's kind of, if you, strong typing means you limit the amount of operations that are possible. That's also why there was one paper by Walter Brown on, we make something like inheriting from double to get a strong type, to get a distinct type that has all the operations of a double. But that's not actually strong typing. That's just giving all the double operations to that strong type, which is in some areas okay-ish, but actually strong typing is about reducing the amount of functionality to only what you need so that you don't get the problems of writing ridiculous code. Like getting a negative Kelvin temperature is not what you want.
Yep.
And that might be, the type should prevent that. Maybe, if it's possible.
Okay, thank you.
So, Hani Sukasan asks, really inspiring talk. Thanks for that. Peter, do you think FOMO, fear of missing out, imposter syndrome drags and gets lost into this never-ending technology boom? So what plays...
I didn't get all of the words. Show it to me again, please. Oh, fear of missing out, FOMO, the imposter syndrome, drags and get lost into this never-ending technology boom. How should we select what one needs and ignore the rest? I would say that I can answer, do the simplest thing that could possibly work. And the fear of missing out, you will never be able to learn everything. But you should be able to learn continuously. So even if you don't like your solution today, when you look at it tomorrow, no problem, refactor it, make it better. If it's simpler, make it simpler. That's the way how to solve the problem of getting better software. Less code is more software. Thank you. Anything else on your list?
Well, you've been talking about TDD, and I know you're involved with unit testing and stuff. So just generally, what are your thoughts on mocking?
On mocking, well, I gave a talk on that and CPPCon, I think 2017. Mocking considered harmful. Mocking should be the means of last resort because it hides dependencies. It actually manifests dependencies that you might not actually need. And that's where what really is a problem. I've seen projects, maybe in Java, where mocking frameworks were used and mock generators were used. I've seen similar things for people using Google Mock. It glues, let's say, it manifests in test cases inner workings of pieces of code that you might want to change in the future, and you can't because then your tests will all fail. That's not the role of test cases. Test cases need to enable change, not fix the code. And for the longer version, watch my video on CPCon video on mocking considered harmful.
Sure. And with that, thank you, Peter.
Thank you for having me.